Welcome back. So we only have how many weeks left for this semester? 2, 3? 2 to 3. Or still have like many weeks? I thought we have only 2 weeks left. Okay, so today we're going to finish chapter 18, right? So next week we're going to go through the midterm 3 hangout thoroughly. Okay, so we're going to review the key concept in each individual chapters. And then in the following week, guess actually the week you are going to take your midterm 3, right? And we're going to have at the same time do the review for your final. Okay, so trying to participate if you can. Okay, and trying to actually ask as many questions as you can during the lectures, because I found it's actually most effective way to use your time. Okay, and many of you. So I know many of you actually use the tutors in the campus, right? So like the lunch and then something else, which I have no idea. Okay. Sometimes they teach you in a way that's not the same as how I teach you. So if that is the case, I would strongly encourage you to follow the way I do, because if you use the way that and then you do not get the correct answer, you can still get a partial credit, right? Because that's actually how I teach you, and I'm responsible for all the things I say. Okay, but if you use someone else's methods that I cannot understand, then you won't actually even get the partial credit. Okay, so trying to follow as closely as you can, and I think most people do pretty well for the midterm 3. Okay, final is actually the one that we didn't do so well. Okay, first is that you have too many courses going to come all together, right? And then it's actually a cumulative exam, so it becomes a lot more challenging for the student. Okay, but if you kind of like really participate all these review sections, I think you'll be actually a lot more prepared. Okay, at least you actually can review the things you are going to see question-wise, okay, for the whole semester in the week right before the final exam. All right. Okay, so let's see, let's have a couple more minutes before we get started. Let me change to the. Okay, so we're going to use periodic table a lot today. Okay, so in order to make sure that you know how to use the periodic table for chapter 8. Okay. All right, so let's get started. Today we're going to finish chapter 18 review, and then the things that we're going to learn about 18, there's actually not much to learn. Okay, and then the things is actually relatively straightforward. So we just go through the basic concept, and then the questions you probably actually encounter for chapter 18. Okay, and first thing first. Okay, the most important thing that we need to learn. Okay, so that we can actually get started with the chapter 18 section to know how to write the things called the atomic symbol. Okay, so basic three parts. Okay, you have this A, Z, and X. Okay, the X is actually the later symbol. Okay, which is going to specify what elements you are going to look at. Okay, Z is always the first numbers you want to actually figure out every time you see a atomic symbol. Okay, so Z is actually the proton number, okay? Indicates how many protons in less specific atom. Okay. A is the mass number. Okay, so this is actually the proton number. A is the mass number. Okay, so the mass number is actually computed by summing up the number of protons and number of neutrons inside your atoms. Okay, so I assume everybody has watched the YouTube video for the chapter 18. But I guess that's just my assumption. Okay, so how many of you have actually have already watched it? Okay, not many. Okay, so a few of you. Okay, so then let's have some recap of all this concept. Okay, so you take chemistry, you take Gen Chem 1, right? Gen Chem 1 is actually talking about the periodic table a lot, right? So you should have some idea about what atom is, right? So what is atom made out of? Yeah, proton, neutrons, electron. Okay, there are three basic particles that forming your atoms. Okay, and then the variation or combination of your atom of your proton and neutrons, okay, give out that periodic table. Okay, and give out all different kind of properties of your atom. Okay, so to define an atom, the most important thing is actually the number of proton and the number of neutron within that specific thing. Okay, so that's why when we write out this atomic symbol or atomic terms, okay, on the bottom left you have the proton number, okay, and then on the top left is actually the mass number. Okay, so the mass number is basically the simple sum of your proton number and the neutron number. Okay, so that's pretty much it. Okay, the electron is too light to contribute to the mass of your atom, so that's why it doesn't actually show up here. Okay, but later on we'll see the electron will play more roles affecting the charge of the atom. Okay, but these are the things that we should know. Okay, something that you need to know the definition is that what is actually an isotope. Okay, so the isotope is actually atoms with the same number of protons, meaning they have the same Z. Okay, but the mass will be different, meaning they have different amount of neutrons inside the atoms. Okay, so those are the very fundamental concepts that you should know. Okay, and then I will strongly encourage everybody, before you actually watch these videos, okay, go watch the YouTube video. There's actually 4 YouTube or 5 YouTube video for this chapter. Okay, each one is like 5 to 7 minutes. Okay, relatively short. Okay, but it actually contains all the necessary information you will need to know. People can actually understand and use all the principles we're going to apply here. Okay. So that's actually the first part that you wish to know. Okay. And we're going to use these rules in the examples. But before we go to there, I want to also emphasize these other few really cool rules. Okay. So in this chapter, one big thing is that you are going to be tested is that if today there's actually one atom got decayed, okay, how will it become? Okay, and then those are the main things that you need to actually do the predictions. Okay, and in your textbook, okay, it's written in a way that's super vague. Okay, even you read the textbook, you won't be able to actually know how to actually make all these predictions. Okay. Here, okay, the item D here is one of the most important things that you should actually know. You should actually memorize. Okay, so this table is purely created by myself. Okay, you won't be able to see these things anywhere else. That's actually my observations. Okay, and then we're going to teach you how to use that table very soon. Okay, but before we go to there, the first thing we want to talk about is this thing's called the decay or the this equation. Okay, so let me highlight this. So we call this as nuclear equation. Okay, you are going to use this equation throughout all these decay processes. Okay, so what this says is actually that if today you have an atom, okay, with defined photon number Z and the mass number A, once it decays, okay, it becomes something else. Okay, in this case, it becomes atom S and atom T. Okay, and each of them has their own photon number and their own mass number. Okay, the things that will always be true is that the A will equals to B plus C, meaning that the original mass number will equal to the sum of the mass number of your product. Okay, so it's what I said right here. A equals B plus C. The same concept apply to your proton number. Okay, Z is going to equals to U plus B. Okay, so this is actually equation, the general equations you are going to use over and over again in all these radial decay processes. Okay, so make sure you know how they actually related, how it actually come from the reactant side transition to the product side. Okay, so let's actually rule number one. Okay, and then when the atoms undergo a radioactive decay, okay, it's going to involve a few particles. Okay, the first particle is so-called the alpha particles. Okay, so that means actually it can during this decay process, it's going to emit this alpha particle. So the things that you should actually memorize that, okay, what alpha particle represents. Okay, so its atomic symbol is this. Okay, alpha particle is basically a helium particle. Okay, once you emit a helium particle, you say let this atom undergo a alpha decay. All right, so that's actually the first particle that you actually memorize. Second one, beta particle. Beta particle is just your electron. Okay, so one thing that's actually unique for your beta particle is that this. Okay, it doesn't carry any mass, right? You can see the mass number is 0. Okay, but for the photon number, it says it's -1, right? Because all the atoms that we see on the table, okay, they're actually neutral. Okay, so if you emit electrons, okay, then meaning actually in your original atom, now it's that become charged. Okay, and in order to make it charged, the only way you can do is actually you have some extra protons inside your nucleus. Okay, proton carries +1 charge, electron carries -1 charge. Okay, so if you have a beta emission, meaning actually you kick out 1 electron from your atom, then inside your nucleus, now you have actually unbalanced proton electron. Okay, so you're going to have the proton number start to show up, and the atoms is going to carry +1 charge. Okay, third one is the gamma particle. Okay, gamma particle is actually very weird stuff. Okay, So you can see the symbol here is that you have this gamma. It doesn't carry any proton. It doesn't carry any mass. Okay. So what is it? You guys heard this gamma ray all the time, right? So it is just a form of energy. It doesn't carry any weight. It doesn't carry any protons. Okay. But we know after you have these gamma emissions, okay, some of the energy will be released, okay, from your atoms. Okay. The very last one is actually called the positron. Okay, so the positron actually has the positive one charge. Okay, but the overall mass is 0. Okay, so positron is actually different from your proton. Okay, so what's the differences between your positron and the proton? Okay, this is actually a proton, neutron, and electron, right? So if you compare your proton and the positron, what's the difference? This to this, right? So what's the differences between the two? Yeah, the mass are different, okay. So for the proton, you carry the mass number 1, right? But your positron carry the mass number of 0. That's actually a major difference between the two. Okay. All right, so these are the 4 Ks you are going to use all the time for this chapter, okay? Okay, so now we need to know, okay, if I give you an atom, how do you know it's actually stable or not, or it's going to undergo a radioactive decay, right? So a few simple rule of thumb that allow you to actually make those prediction, okay? The first one is that if you have the even number of proton and neutron, okay, they will be more stable. Okay, so this is actually one rule that you have to bear in mind, okay? If you have even number of proton and neutron, then the atom tend to be stable. Okay. With that being said, what implies that if you have a odd number of proton and neutron, then the atom is not stable. Okay, everybody got the things I just said? Okay, so the even one, good. Odd one, no good. Okay, so those are like very fundamental things that you should actually know. And then to be more, no, proton number is actually even. Neutron number is even. That's the most, yeah, individually. Okay. Okay, so there are some special cases that are actually extra stable, okay, which I point out here. Okay, so if you have a proton number is 2, A, 28, 82, 20, 50, 126. Okay, if you see the proton number give you those numbers, but extra stable atoms. Okay, so it's not too difficult to memorize. 2A, 28, 82, right? 50, 20, 50, and 126. Okay, so those are the really stable one. Okay, so if you see a questions give you a atomic symbol where it gives you all this matching number of protons, then they will be very stable. Okay. All right, so now you know a few simple cases that it is going to be very stable, right? But what are the ones that's going to decay? Okay, what is the one that is actually not stable? Okay, so this is actually the things get very interesting, okay, because this is actually the part that most students get so confused. Okay. The rule of thumb is actually that if the differences of your mass number and then the atomic mass, if the difference is larger than 2, then it is not stable. Okay. So mass number and atomic mass is larger than 2, then it is not stable. Okay. So I assume by now everybody know what mass number is, right? It's actually the top left corner, right? So we use the symbol A to represent that, right? So that is actually the mass number. Atomic mass, how do you get the atomic mass of an atom? Yes, okay, so this actually time you want to be actually a really good friend as your periodic table, okay? So, for example, that is actually your atomic mass. Okay, so if I give you a atomic symbol with a certain mass number, and I ask you, is this atom stable? Then what you do is actually you compute the difference between your mass number and the atomic mass from your periodic table. Okay, if it's larger than 2, not stable. Is that clear? Okay, so let me write the things down. Okay, so the atomic mass is from your periodic table, okay? Okay, so let's actually the first thing that if you compare the difference between the two is larger than 2, then you know you have a non-stable atom. Okay. The other one is actually if you have your Z, which is actually a proton number, larger than 83. Okay. So your Z larger than 83, they won't be stable. Okay, so those are the things that people have observed so far. Okay, so if Z is larger than 83, then it's not going to become stable. Okay, meaning if you look at your periodic table, where's actually 83? It's 83, right? Anything beyond that atom, they are all radioactive. Okay, they're going to decay. All right, so those are the things that you should know. Now come to the most interesting part. Okay, so besides the case we have talked about, okay, if I just randomly give you one atom, okay, that doesn't belong to any case they have discussed, okay, and I ask you, if this atom is undergoing a radioactive decay, okay, what kind of decay you are going to have? Okay, so we have 4 different decay, right? Alpha, beta, gamma, and positron, right? So those 4, right? How to actually assign different decays to a given atom is actually the things you need to be very careful about. All right, so this table is my table, okay? I actually look into the textbook very carefully, and then after I did enough of questions, then I realized, okay, this is actually the table that's going to work for everybody. Okay, the way you use it is actually you want to use things called the N to Z ratio. Okay. Well, the N is actually your number of neutrons. Okay, so let me write these things down. So this will be your neutron number. Okay, Z will be your proton number. Okay. So the way you use this table is actually you want to actually group. Okay, first you need to know what kind of atom that you have. Okay, so here I separate the atom into 4 different types. Okay, if your Z it belongs to 1 to 20 is one type. Okay, 2 to 40, 40 to 83, and larger than 83. There are 4 types of different atoms. Okay, to calculate the N to Z ratio, okay, each of them have different threshold. Okay, and the threshold is actually 1, 1.25, 1.5, and 1.6. Okay, so if you calculate the N to Z ratio, for example, if today I have an atom where the Z equals to 25, okay, then I know I need to actually use the threshold of 1.25. Okay, if I calculate N to Z ratio of a specific atom, if it is larger than the threshold, okay, then you are going to have beta decay. Okay, you're going to have beta decay. It's actually larger than the threshold. Okay, so when it's a beta decay, meaning you're actually generating one electron. Okay, you generate one electron at the product side. Okay, everybody follow so far? Okay, so if today you actually have your N to Z ratio below the threshold, okay, then these three will have positron emission, meaning you have a positive electron at the product side, or you have electron capture, meaning you have an electron on the reactant side. Okay, so let me write this down so maybe you can see better. Okay, so let's say, okay, beta decay is actually you're going to produce electrons on the product side, right? So this is actually what it means. If actually is smaller than the threshold, okay, you either have the positron capture. Positron emission, meaning you have a positive electron on the product side, or this thing is actually equivalent to electron capture, right? So these two is actually equivalent. Okay, so this is actually electron capture. That is actually positron emission. Okay. So depending on your photon number, the threshold will be different. Okay, so you have to make sure you use the correct threshold to predict is actually above or below the threshold. Okay, and then if you have a photon number larger than EP, okay, and then if it is actually below your threshold, then you're going to have a alpha decay, meaning your helium is going to show up at the product side. Okay, so meaning it's going to be AZ and then undergo. Yes. Okay, it will show up at the product side. Okay, so those are the first sets of knowledge that you need to use, okay, to do a few, to answer a few questions you're going to encounter this week. Okay, so let's go through a few examples so we can see these things better. Okay, question number 1. So it's actually a true-false question. Okay, it says nitrogen 17 is expected to be stable. Okay, so here, once you see the things, okay, so nitrogen 17. Okay, what does that 17 means? What is the number? It's the mass number, right? Okay, so the first thing you do is actually to figure out what is the photon number, right? So the photon number will be actually just the index on the periodic table, right? So if you look at this, nitrogen. Okay, so the mass number is 17, right? And then the atomic mass is what? 14, right? So we can't use our rule number 1, right? So we didn't actually, at this moment, we don't need this yet, okay? Okay, so to predict whether it's actually stable or not, we first actually compute the mass differences, okay? So we need to know what is actually the atomic mass first. Okay, and then from the periodic table, we know it is 14.0, right? Therefore, we can use the mass number minus your atomic mass. Okay, so they will equals to, the mass number is 17. The atomic mass is actually 14. Therefore, you have the mass differences equal to 3, right? Which is actually larger than 2. Therefore, we know it's an unstable species. Okay, so let's actually how you solve the first question. All right, so similarly, we're going to do the second one. Okay. Arsenide, okay, 74. Okay. First, check out what is actually the atomic mass, right? So AS right here, right? So 74.922. Okay. 74.92. Okay. Therefore, if you compute the mass number, in this case, actually 74, minus atomic mass is 74.92. Okay. We only care about the differences. Therefore, it's absolute value, right? So if you do that calculation, you'll get a value of 0.92. Okay. Therefore, it is stable. Okay. Next, aluminum 24. Okay, and then if you check out the atomic mass of aluminum, which is 26.98. Okay, so 26.98. Okay, so you're going to calculate the difference between your mass number and then the atomic mass. This will give you a value of 2.98, which is larger than 2, therefore unstable. Okay. That the absolute value. Yeah, you mean you're talking about this, right? Yeah, so I take absolute value because you care about actual differences. Okay, the sign is doesn't really matter. Yeah, just the change. Okay, so the very last one, we're going to check out the BI 209. Okay, so if you check out the BI, then you're going to see the value is actually 208.98. Okay, so atomic mass actually 208.98. Okay, therefore the difference between this is actually 209 minus, sorry, 208, not 298, sorry, 208. Okay, so this minus 208.98. So difference is actually 0.02, smaller than 2. Therefore, it is stable. Okay, so this is actually the first things. Okay, so if you give you an atom with a mass number and asks you whether it's stable or not, okay, then the things you do is actually compute the difference between your mass number and the atomic mass. If it's larger than 2, unstable. Smaller than 2, stable. Okay, that's
Say one of the other things, so like if it gives us something automatically is it Z has to be greater than 83? Like, I guess we wouldn't know from there, but like,
yeah, so if you actually know the Z, then you can use the Z as another way to predict.
oh, okay.
Right, but here apparently it just only give you the mass number, right? So it's not a hint telling you that I want to compute the difference between the mass number and the atomic mass. Yeah. Okay, so let's actually the question number 1. All right. Okay. Number 2. So this is actually the part that most students will get confused. The first question says, the Y95 is radioactive. Which mode of decay will be expected for this nucleus? Okay, so first, okay, Y95, okay, you need to actually translate. Okay, like 95 is actually the mass number. Okay, every time you see an atom dash a number, okay, in this case, Y dash 95, right? Let 95 is the mass number. Okay, so this is actually your mass number. Okay, so I would suggest that you try to write the things out like this. Y95. Okay, then you start actually looking for Y. Where's actually your Y? 30, 39, right? So you know the proton number of your Y is 39. So just in case that not everybody sees the periodic table. Okay, so okay, you see, you find the Y from the periodic table, you will see how many protons it will have. Okay, so the number on top of the Y is actually your proton number. Okay, so that means this is actually the atomic symbol for your Y. Okay. All right, then it tells you that this guy is not stable. It's going to undergo a radioactive decay, right? And actually predict which kind. Okay, so there are 4 different kinds, right? So this is actually the time that you use the table that I create. Okay, first, identify what is actually your proton number. 39, right? So if you go back to the table, then you will know it belongs to this group, right? It's 1 to 20, 20 to 40, 40 to 83, and larger than 83. That only 4 groups. Okay. Right now you're going to the group number 2, right? So the threshold you're going to check is what? 1.25 is actually a threshold, right? So we can actually go back. So you know the proton number equals to 39. Therefore, the threshold is 1.25, right? So what is the thing you compare to the threshold? It's actually the neutron to proton number. Okay, so you know your neutron number is going to equals to your mass number minus your proton number, right? So it's going to equals your mass number minus your proton number, which is going to equals to 95 minus 39. And this will give you a value of 56. Okay, so that you know, for this specific atomic symbol, you have 56 neutrons, right? Then you start to calculate your N to Z ratio, okay? So the N to Z ratio is basically just your number of neutron over number of proton. Number of neutron is 56. Number of proton is 39. And then once you calculate that number, you got a value of 1.44. Okay. Once you got this N to Z ratio, then you start to compare to its threshold. Okay, so you know your N to Z ratio is larger than the 1.25, right? Okay, so since you know it's larger than 1.25, okay, go back to our table. It says it's larger than the threshold, right? So the decay we expect to have will be the beta decay. Okay, so you know you're going to have a beta decay. Okay. So this is actually how you start to use that table. Yes. So 1.25 is actually the value that I specify in the table. Okay. So the threshold is go from 1, 1.25, 1.5, and 1.6. Those are 4 values that you need to actually remember, so you know which threshold to compare to. Okay, and all this value is actually after I reading through your textbook very carefully and I see enough of decay, I summarize it. Okay, so that you can have all this number to make this quick comparison, understand, and be able to predict how much decay you're going to have. Okay, if you just read your textbook, you're not going to see this. Okay, and then I found that students become super confused. They don't know how to predict. Okay, but this one is actually very useful. Okay, so use this table as much as you can. All right, so only 4 group, okay? 1 to 20, 20 to 40, 40 to 83, and larger than 83. That's actually my personal summary. Like I say, I read through your textbook many times for 7 years. Okay, I do all the homework problems for you and realize this is actually table that you should remember. Okay, you won't find these things anywhere. That's actually my own creation. Okay, but this one I think is actually very helpful. Especially when you do your homework, you'll realize this one is actually very powerful. Okay. So strongly encourage that you actually memorize this, because all you need to remember is actually 4 groups. Each group has their own threshold. Okay, threshold comes from 1, 1.25, 1.5, 1.6. Relatively easy to memorize, right? And then if larger than threshold, only one possibility, beta decay. Okay, if small, okay, group 1 to 3 tells you either have your electron emission or positron emission or the electron capture. Okay, if you have a Z larger than 83, then you're going to have a alpha decay. Okay.
So 1.5 right next to it, you think it is less than 1.5, is it electron capture or is it positron emission or?
Electron capture and positron emission, they are actually equivalent. Okay. So for group 1 to 3, you actually have the same, it's the same result. Okay, group 4 is actually the one and the only one that's undergo a alpha decay. Okay, so it's actually smaller than the threshold. All you have will be the beta decay. Okay, so this is actually the most valuable tables for chapter 18. Okay, if you can memorize this table, you can actually solve many of the confusing problems in chapter 18. Okay.
It depends on which side of the reaction we're on.
What do you mean?
Says that it's electron capture at the reactant side.
Yeah, so this two is actually equivalent. So this one is the positron emissions, right? This one is actually electron capture. So either or. Yeah, either. Either this or that. Okay. All right, so let's do a few more practice so you can actually get familiar with the rules that I just bring up to you. Okay. So this is actually another question, right? How would EU-141 be expected to decay? Okay, so EU-141, right? So you need to analyze the things that you have here. Okay, so what is actually the proton number of your EU? If you look at the periodic table, EU is 63, right? So EU is actually right here. 63. Okay, just want to actually point out so that everybody know where to find your atoms. Okay, so EU is 63, right? That means actually your proton number is 63, right? All right, so proton number 63. Neutron number will be 141 minus 63, which is going to give you a value of 78. Okay, so the N to Z ratio will equals to 78 divided by 63, which is going to equals to 1.24. Okay, so let's actually N to Z ratio of this specific atom, right? Now I want to actually look at, okay, what is the threshold that we should use? Okay, remember how we do is actually 1 to 20, 20 to 40, 40 to 83, 8 and above 83, right? 4 different group. This one will belongs to your group number 3, right? So the threshold for the group number 1 is actually 1, 2 is actually 1.25, 3 is actually 1.5, right? So you know this is actually smaller than your threshold, right? So if it is smaller than your threshold, what do you expect? Yes. Okay, so let's go back to the table. Okay, you really can memorize this. Okay, it's actually smaller than the threshold. Okay, in group number 1, 2, 3 is actually you either have positron emission or the electron capture. Okay, so that is actually the answer that we want to put here. Therefore, okay, so positron is this. Okay, positron emission or electron capture, right? Okay, so that's actually how you solve this problem. Okay, you can see the question actually doesn't provide too much wording, right? Just give you atom and actually what the decay is, right? But the underline, the way I actually solve this is actually using a table. Okay. That's very good questions. Okay, what happens if the number just fall in between, right? So I say 20 and then 40. Right, so you can see here. Right, what happened is actually 20, 40, or just 83, right? I have no answer to that. To be honest, because I never actually see a question like that. They will actually fall into a very confusing zone, right? And then it's very difficult to actually provide a straightforward prediction, right? So you should know that, okay, what is the name of this course? General chemistry, right? What is the things you need to learn? The general rules, right? So sometimes, okay, not just sometimes, many times, we always encounter some special case. Okay, but that's not the main goal here, right? The main goal here is actually, okay, can actually reasonably predict what's going to happen. Okay, and then the one that I cannot predict become very interesting, right? And that's why that's actually what the researcher is trying to actually figure out. That's actually answer they can actually accept. Okay, cool. All right, so let's do one more. Okay, so that we can really get familiar with all the things. Okay, which mode of decay would be expected for the nucleus of AT12? Okay, so again, AT212, right? Therefore, you know that 212 is actually your mass number, right? And then if you check out your periodic table, the AT is going to have a proton number of 85, right? It's right here. Okay, so you know this will be 85. Okay, so N to Z ratio. Okay, so okay, slow down a little bit. Proton number 85. neutral number 212 minus 85. They give you a number of 127. Okay, so the N to Z ratio is going to equals to 127 over 85, which give you a value of 1.49. Okay, so the total number is actually 85, right? So 85 belongs to group number 4, the very last one, right? Okay. As long as it's actually larger than 83, it belongs to group number 4. Okay, so the threshold for your group number 4 is 1.6, right? So smaller than your 1.6, right? So if you have smaller than 1.6, you are going to get the alpha decay. Okay, therefore, okay, so let's actually how you solve this. All right, so use that table, okay, as much as you want, because this is actually a portion that going to encounter a lot in this chapter. Okay, and that is actually a way I can provide to you to solve this kind of questions. Okay, so I guess that's how I will leave this to you. Okay, you can actually try to. Oh, okay, so this one is actually an easy one. We can actually go through this one quickly too. So the very last one is actually says V47 can undergo electron capture. What is the product nucleus? Okay. So here is actually the one we use the nuclear equation. Okay. So first thing first, V47. What you need to do actually to write out its atomic symbol. Okay, V47. Okay, so what is the photon number of V? Okay, so V4723, right? And it says undergo a what? Electron capture. Okay, so that means actually this atom is going to capture one electron, right? So you need to know how to write out the atomic symbol of electron. That's right. Okay, so you're going to get something new, okay, and then you don't know its atomic symbol. The later you don't know yet, okay, but you do know 47 plus 0, therefore the mass will still be 47, right? Photon number 23 minus 1, it becomes 22, right? So what is actually the atom at the photon number of 22? Will be titanium, right? That's why you put titanium right here. Okay, so if you just write out in the traditional way, that's why you get this Ti47. Okay, again, the 47 is actually the mass number, right? So you need to know how to actually use your nuclear equation. Okay, understand what it means by electron capture. Okay, so electron capture means actually it's going to gain one electron, right? How about positron emission? It's going to have a E. No questions? Okay. So if you see the question says, okay, these things actually undergo a positron emission. Okay, when you see this word emission means actually it's something being produced, right? That means actually to put your positron on the product side, not the reactant side. Okay, and then again using the same relationship, okay, the sum of the mass number, okay, of your reactant should be actually the sum of mass number of your product. Okay, the sum of the proton number of your reactant should be equal to the sum of proton number of your product. Okay, yes. Yeah, that is the same thing. Yeah, that's why I say the electron capture and the positron emission, they are actually equivalent. Okay, so if you look at the table again, I actually So it is either this or this. They're actually equivalent. So positron emission is equivalent to the electron capture. Okay, but for the positron emission to actually put the positron on the product side, electron capture put the electron on the reactant side. All right, so let's actually the thing. Okay, so let's practice a little bit about this nuclear equation. You are going to have CF244 plus 2 neutrons. Okay, neutrons, you should know the atomic symbol is this. Right? And they say this is actually some nucleus that we don't know. Okay, we don't know what it is, but it reacts with a alpha particle, right? So what is alpha particle? Alpha particle is your helium, right? So, okay, so you need to actually get familiar with these 4 different types of particle. Okay, so you can actually write all this equation without any problem. Okay, so the things you want to know further is actually what is actual proton number of your CF, right? So if you look at the periodic tables, the CF has a proton number of 98. Okay, so everybody see that? Either side, okay. Number equation you can actually have. Okay, therefore you know your A should equals to 242, right? Okay. Similarly, you can write your proton equation. Okay, proton number equation. Z plus 2 is going to equals to 98 plus 2 times 0, right? Therefore, you know your Z will equals to 96. Right? So once you know your Z is 96, right? Then you go back to your periodic tables. Okay, what is actually the letter you are going to have? Yeah, right? So you know this guy will be your CM, right? Therefore, you know the atomic symbol you're going to have will be 242, 96. This is actually how we figure out the answer. Okay, so make sure you know how to actually write the nuclear equation. Okay, once you know, it's actually very straightforward, very simple. Actually, something that's actually very interesting. Okay, this is the next topic we want to discuss. Decay kinetics. Okay, that's actually another important thing in chapter 18. Okay, and some of the question actually looks very confusing. Okay, and this is a part that you want to actually pay close attention. There's actually only one questions that you're going to use for calculate all this decay. Okay. Natural log AT over A naught equals to negative AT, negative KT. Okay. So the A naught is what? the initial amount of atom. Okay, so initial number of atom. Okay, or initial atom number. Yes, that's easier. Okay. The AT is number of atoms at time t. Okay, so this is actually the remaining one. Okay, so this is actually the remaining atom number at time t. Okay, so the ratio of lag, you take negative log, take the natural log, is going to equals to negative k. K is actually the decay rate constant. Okay, T is simply the time. Okay, so we learned these things in chapter 15 or 14, forgot. Okay, but we'll go through this one in the future when we do the review again. Okay, but this is actually equation that you can actually memorize for this chapter. Okay, natural log AT over A naught equals to negative. Don't forget about the negative sign. Okay, negative K times T. Okay, so this is actually the only thing that you need to actually know. Okay, to elaborate these things a little bit more, that is actually more relevant to the question that once this atom evolve, it undergo a decay to produce another one. Okay, then in your system now, you're gonna have multiple different species, right? But the things that you should have in mind, like all this decay is per atom based. Okay, it's actually if let's say one atom got decayed, it's going to produce one product. Okay, so that means if today I have 100 of atoms to start with, okay, after a certain time, I got 70 of my original reactant. I'm going to have 30 product. Okay, the total number of atoms will still be the same. Okay, everybody follow that? That's actually very important concept you should know. All this decay is per atom base. Okay, so if one atom got decayed, it's going to produce one product. Okay, that means actually if you sum up the total number of your reactant and product, that's your original atoms you have. Okay, that will be actually your A0 or A0. Okay, so that's actually something that very important so that you can actually understand the logic when we solve the problem for question number 4 or 5. Okay, question number 4 and 5. Okay. All right, so let's look at the simple one, question number 4. Okay, so we can get ourselves familiar with how to apply that specific equation. Okay, so the first sentence of question number 4 says the CCN137 undergo beta decay and have a half-life of 30 years. Okay, half-life of 30 years. Okay. How many beta particles are emitted by a 14-gram sample of CCN in 3 minutes? Okay. So when you first read these questions, okay, it's not very clear how you should handle the question. Okay. So we need to actually break apart these questions into 2 parts. Okay. Apparently, this is actually a decay type of questions, right? It tell you the half-life is certain amount of time, right? So I assume everybody will have no problem to, right? Okay, so that is actually a question you're going to use, right? Then it says the half-life. Half-life means actually half of your reactant got consumed. Okay, that means actually at this specific time, the concentration of your A will be just half of your original concentration, right? So that's actually what half-life means. Okay, so this is something that you can know. Okay, so, and it tells you this is takes 30 years. Okay. So with all this information put together, you should see that since your AT is 1/2 of your A naught over A naught equals to negative K times 30, right? So A naught will cancel out. Therefore, it becomes natural log 1/2 equals to negative K times 30, right? So the first sentence is trying to do what? Trying to tell you what your K value is. Okay, I hope that everybody can see this. Okay, so first sentence, what it is trying to tell you is actually compute K first. Okay, so what is the unit of your K? So the natural log is actually unitless, right? That means that your K times your T has to be unitless. What is the unit of your T? Years, therefore your K will be per year, right? But if you look at your question in the very end, it asks you in minutes, right? So you can actually convert your year into minutes, so you can have your K as a unit of per minute. Okay, so that's actually what we're going to do first. Okay, so 30 years. Okay, 1 years you have 365 days. Each day have 24 hours. Each hours you have 60 minutes. Okay, so those are the things that you to do. Okay, so by doing this, then you can get your K is going to equals to 4.4 times 10 to the negative 8 per minute. Okay, so that's actually the first information you can get from the first sentence, first half of the sentence. All right. Now it starts to ask you how many beta particles are emitted. Okay, after in 3 minutes, right? Okay. So now you know natural log AT over A0 equals to negative K. Right now you know the number 4.4 times 10 to the negative 8. And then you know you want to do for 3 minutes, right? So on the right hand side, you actually have all the information that you need. Okay. So now, how are you going to write the things on the left hand side? Okay. So remember what I say before I actually jump into this. Okay, I say all the decay is per atom based. Okay. Does this question tell you how many atoms you have? It doesn't, right? It only tells you what? The mass of the substance that you have. Okay, so can you actually convert the mass of the substance into number of atoms? Yes, you can do that, right? It's actually relatively simple, right? So what you do is that your A0, okay, which is actually number of atoms, can be calculated using 14 gram, right? What is actually the mass? CCM 137, right? So you just divide it by 137. That's actually how many moles of that atom you have, right? And we also know for 1 mole of atoms, you have 6.02 times 10 to the 23rd. You have that many atoms. Okay. All right. So once you do that, then you can actually get a number of 6.15 times 10 to the 22nd. Okay. So you have that many atoms. Okay. So once you have that, you put it back to this equation. Okay, therefore you're going to get natural log AT over 6.15 times 10 to the 22 is going to equal to negative 4.4 times 10 to the negative 8 times 3. Okay, so by doing this, you should be able to solve your AT without any problem. Okay, so once you solve for your AT, you should get that. You are going to get 6.14999188 times 10 to the 22. Okay, so you got this AT, right? So the AT means what? Means the one that is not decayed, right? That is actually the one that still remains. Okay. Therefore, to figure out the number of decay that you have, then you should calculate the difference between your A0 and the AT. Everybody follow this logic? Yeah. So once you do the calculations, you are going to get a value of 8.1 times 10 to the 15. Okay, so that means actually you have occurred that many decays. Okay, so that is actually you're going to produce that many particles. Okay, so that is actually how you figure out the answer of these questions. Okay, so the key is that you should know that the A is actually the number of atoms. Okay, not the mass of the atom. Yeah, 6.150000 minus 6.1 minus 6.1499999188. So you can see the order is actually changed quite a bit. Oh, no. Yeah, but you start with 22. No. Okay, let's write the things down. 6.15. Okay, 6.14. 9999188. What do you get? 0.000000812 times 10 to the 22nd. These things give you that 15. Is that clear? Yeah. So when you calculate this type of questions, okay, make sure you actually put enough digits. Okay, so when you do that calculation, you still get some meaningful numbers. Okay. Otherwise, if you actually did not operate your calculator properly, the number you got will be actually very off. Okay. Again, the most important thing in this specific question is actually when you use less specific equations, the things that you should use is really the number of atoms. Yes. Six point 1499. Actually, that number is A0 or AT? How do I get which one? You're fine? This is Avogadro number. You mean this, right? So this is actually a constant will be provided inside your table, actually. So it's right here. That means actually how many atoms per mole. Right. Let's say the number will be provided when you do your exam. Okay, so everybody follow the things okay? Okay, so we're going to use hopefully we can use the very last 5 minutes to finish this question number 5, which is actually the most difficult question you probably will encounter for this chapter. Okay, so let's look at this. A rock contains 0.275 milligram of lead-206 of each milligram of uranium-238. the half-life of the decay of uranium-238 to lead-206 is 4.5 times 10 to the 9 years. Okay. The rock was found how many years ago? Okay, so it sounds actually pretty complicated, right? But again, it's actually interesting to think about at the per atom level. Okay, so here what it says actually always provide the mass, right? It says I have how many mass of A in how many mass of B, right? So in this case, it says you have 0.275 milligram of lead 206, right? In 1 milligram of uranium 238, right? So this is actually a mixture of your reactant product, right? So what you need to do is what? First, you actually need to know how many atoms you have for each species, right? So the way you figure it out is that you need to calculate the moles first, right? So 0.275 times 10 to the negative 3. So you convert that into grain, right? Divided by the molar mass is 206, right? Multiply 6.02 times 10 to the 23. Okay, and that is actually how many atoms that got decayed. Okay. Similarly, it's actually 1 milligram, right? 1 times 10 to the negative 3 divided by 238 times 6.02 times 10 to the 23rd. Okay, so let's actually how many atoms that you have within the mixture. Okay. So this means, okay, let me give you the number here. So once you do this, can someone calculate the number for me? I only calculate how many more. 8.036 times 10 to the 17. How about the bottom one? Times 10 to the 21. No, 2.2 decimal is fine. Yeah, but is that the correct number? Everybody get? So this is 21. Looks a little bit odd to me. It shouldn't be let 21. 18. Yeah. Okay, so what does this tell us? Okay, so the one that got decay is let many atoms, right? The one remain is 2.53 times 10 to the 18th, right? What does this tell us? Okay, now we want to actually put this back to in the equation we have, okay? Natural log AT over A0 equals to negative K times T. Okay. What does that 8.036 times 10 to the 17 tell us? So what's that? The lead, right? Lead is actually the product, right? It's actually uranium decay become lead, right? So lead is actually a product. So that actually tells you how many decay you already have, right? The bottom one is actually the remaining one, right? So the remaining one you have 2.53, right? So it means actually what is actually A0? The sum of the two. Everybody get this? This is actually the decayed. Yeah, how many decades that you have, right? And then this is actually the remains. Okay. So remains is what? Your AT. Okay. The sum of the two will be your A0. Right? Because once you actually decay, then you produce less many, it means actually in the beginning, you need to actually summing up. Okay. Everybody follow this? How many of you did not get this? It's actually probably one of the most important concepts for this question. Okay, first, it's actually going to convert into atom. Okay, then you know how many products you have, how many reactants you still remain, right? The remains one is actually your AT, right? And to calculate your A0, you need to just sum up your product and reactant. Okay, so with that being said, you know the things you should have is actually a natural log. AT is 2.53 times 10 to the 18. Okay, A0 will be 2.53 times 10 to the 18 plus 8.036 times 10 to the 17. Okay, so there will be actually the things that you should have on the left-hand side. Okay, on the right-hand side, do you have the K? Do you have the K in the question? Yes. So let's actually it says the decay, the half-life. Okay, so no, you don't actually have life yet. Okay, but you can actually calculate it, right? It says the half-life of the decay of lead takes 4.5 years, right? So that means actually half means actually natural log 1/2, right? Equals to negative K times T is actually 4.5 times 10 to the 9. Okay, again, you can use that relationship to calculate your K. Okay, so when you back calculate your K, you should get the K is going to equals to 1.54 times 10 to the negative 10 per year. Okay, so this is actually where you can get your K, right? So you put into this equation negative 1.54 times 10 to the negative 10 times your T, okay? And the T will tells you this rock was born in that many years, okay? So if you calculate your T, okay, so if you compute your T, you should get a final answer of 1.79 times 10 to the 9th power years. That means this rock was formed in that many years ago. Okay, and this is actually the way how the scientists actually dated how old a tree is. Okay, so it's actually we compare the mass of your product over your reactant. Okay, and using this way to actually figure out how old it is. All right, so let's say for today, and then I think on next Tuesday, we're going to finish chapter 18, okay, including all the contents for your final. Then we'll start to review your midterm 3. Okay, so let's say for today, thank you. Give me a second.